All the files uploaded by the user have been fully loaded. Searching won't provide additional information. Pressure gauges for reliable, localized pressure monitoring in industrial applications. Functionality and measurement principle. Pressure gauges offer direct, visual indication of process pressure using the deformation of a sensing element, typically a Borden tube, to drive a pointer across a calibrated scale. This mechanical method ensures passive operation without power requirements, making pressure gauges ideal for simple, fail-safe pressure monitoring in pipelines, vessels, and equipment. Applications and selection context. Pressure gauges are best used when local pressure indication is required for operator decision-making. The process doesn't justify or require continuous electronic transmission. The instrument must operate without dependence on power or signal infrastructure. Monitoring needs to continue during control system downtime or field isolation. Their utility is prominent in standalone applications, e.g., boiler feed lines, pump discharge, supplementing transmitter-based systems as a passive local readout. Pressure points used only occasionally for troubleshooting or commissioning. Design specifications and sizing practices. Gauges must conform to EN 837-1 and be of the safety pattern type to ensure operational protection in case of rupture. The selection of scale and range must match both normal operation and system safety requirements. Normal pressure should fall between 50% and 75% of full scale. Scale must also account for low design pressure, e.g. vacuum conditions, and upper design pressure, e.g. relief valve set point. Standardized range series in bar Josh, positive 0 to 1.6, 0.5, 6, 10, 16, 25, 40, 60, 100, 160, 250, 400, 600, 1000, 1600. Vacuum 1 to 0. Compound, Diage 1 plus 0.6, plus 1.5, plus 3, plus 5, plus 9. Narrow range varieties must still accommodate full safety margins. In systems with normal pressure far below design limits, gauge savers or snubbers should be considered. Construction and protective features. Nominal diameter, standardized at 100 millimeters unless specified otherwise. Material choice. Standard Borden gauges are stainless steel or brass. In corrosive or plugging-prone services, use diaphragm-sealed gauges. See diaphragm seals. Oil filling. Discouraged for environmental and maintenance reasons, use only with principal's approval. Mounting. Preferably panel-mounted or on instrument stands with clear visibility from operator locations. Special configurations. Diaphragm seals, required in services involving corrosion, solids, or sanitary conditions. Must be supplied integrally with the gauge and constructed without screwed connections. Gauge savers. For pulsating pressure or pressure spikes, protect the gauge with a snubber or restrictor. Vacuum and compound gauges, necessary in services where pressure can swing across vacuum and positive ranges, such as suction lines or certain vented vessels. Advantages in plant design. Immediate, readable indication, no signal transmission delays. No dependence on external power or control systems. Long service life with minimal calibration drift. Easy troubleshooting and maintenance by field personnel. Limitations and mitigation measures. Subject to mechanical wear, especially in vibrating or pulsating services. Use snubbers or damped movements. Inaccuracy under extreme temperature shifts or exposure to chemicals. Use diaphragm seals and remote mounting. Prone to clogging in viscous or dirty services. Incorporate flushing ports or diaphragm protection. Accessibility and location considerations. Pressure gauges must be mounted where operators can view them without obstructions. According to minimum accessibility standards, permanent access is mandatory for all IPF-related gauges and frequently read indicators. Infrequently used gauges, e.g. for maintenance, may be located in less accessible positions but must still comply with safe approach standards. Conclusion: pressure gauges remain essential for robust, localized pressure indication in modern plants. When properly sized, selected, and installed with attention to service conditions and accessibility, they offer high reliability with zero operational cost. In critical, corrosive, or pulsating environments, enhanced versions with diaphragm seals and gauge savers extend their applicability even further, ensuring operator confidence in pressure visibility at all times. Temperature instruments for precision thermal monitoring in demanding process environments. Functionality and measurement principles. Temperature instruments detect and quantify process temperature by sensing thermal-induced physical changes. Depending on the principle, they convert heat into mechanical displacement, voltage, or resistance, then display or transmit the result. Most sensors are installed in thermowells to protect them from process media and allow replacement without depressurization. Key temperature instrument types: thermocouples, TCs, use dissimilar metal junctions to generate thermoelectric voltage. Best for high temperature, fast response applications. Tolerate harsh and vibrating environments. Resistance thermometers, RTDs, typically PT100, measure temperature by resistance change in platinum wire. High accuracy and stability over time. Suitable for precise control loops and custody transfer. Bimetal dial thermometers. Mechanical coil expands with temperature to move a dial. Local passive indication, no power needed. Preferred for temperatures up to 400 degrees Celsius. Infrared optical pyrometers, non-contact temperature sensing using emitted radiation, useful in very high temperature zones, e.g. furnace tubes. Filled thermal systems, with approval, passive mechanical systems using vapor or liquid expansion, limited to legacy or specialty applications. Typical applications by instrument type: thermocouples, furnace tubes, stack monitoring, skin temperature, fast dynamic measurements, e.g. combustion. RTDs, reactor jackets, product blending, custody metering, differential temperature and narrow span measurements. Dial thermometers, utility lines, tank shells, local monitoring where power is unavailable. Infrared pyrometers, radiant surface monitoring, rotary kilns, refractory linings. Selection and installation considerations: temperature range, RTDs up to 650 degrees Celsius, thermocouples, type KB, up to 1600 degrees Celsius. Bimetal, typically 400 degrees Celsius. RTDs, Class A tolerance, IEC 60751 for high precision. TCs, Class 1, IEC 60584-2 for standard process use. Bimetal, -1 to 2% of full scale. Environmental resistance. TCs perform better in vibration, hydrogen-rich, or oxidizing surfaces. RTDs require protection from vibration and surge currents. Thermowells must match velocity, corrosion, and mechanical loads. Thermowell use, standard for all immersion sensors, TCs, RTDs. Prevent breakage and allow removal under pressure. Must be installed at sufficient immersion depth to avoid temperature lag. Advantages over other temperature sensing methods: broad temperature range coverage from cryogenic to 1500 degrees Celsius. High reliability with proper protection, thermowells, insulation. Adaptable for point, profile, or average temperature measurement. Available in duplex form for redundancy or split output with caution. Limitations and precautions. RTDs degrade in high vibration or over temperature conditions. TCs can lose calibration with oxidation, especially in reducing atmospheres. Thermowell vibration vortex-induced may cause fatigue. Design must meet ASME PTC 19.3 TW criteria. Response time depends on immersion length, thermowell mass, and process fluid velocity. Good practices for installation. Position sensors in fully immersed locations away from mixing zones or dead legs. Avoid locations near flashing valves or rapid phase change zones. Use angle-mounted thermowells in large vessels to achieve immersion depth. For skin-mounted applications, ensure solid metal contact and thermal insulation. Conclusion: temperature instruments provide foundational data for thermostat safety, efficiency, and control. Whether using rugged thermocouples, precise RTDs, or mechanical indicators, proper selection, protection, and installation ensure long-term accuracy and plant reliability. With no moving parts and extensive compatibility with control systems, modern temperature instrumentation remains a cornerstone of industrial process monitoring. Resistance thermometers, RTDs, for high accuracy temperature measurement in industrial processes, functionality and measurement principle. Resistance thermometers, commonly referred to as RTDs, IAs, measure temperature based on the predictable increase in electrical resistance of a metal, typically platinum, as temperature rises. The most widely used type is the P100, which has a resistance of 100 ohms at 0 degrees Celsius. RTDs are known for their excellent accuracy, repeatability, and stability across moderate temperature ranges. Core characteristics of RTDs: Sensing element, platinum, PT100 standard, optional PT500, PT1000 for high accuracy applications. Follows IEC 60751 resistance temperature relationship. Tolerance Class A standard or Class B depending on precision requirements. Temperature range, typically Co200 to plus 650 degrees Celsius, can exceed 650 degrees with specialized construction, but accuracy may decline. Accuracy, Class A no 02 times TT Adregis Class B minus 03.05 times Tanqueray, far superior linearity and repeatability compared to thermocouples. Applications and use cases, preferred for custody transfer, e.g. fiscal metering temperature correction. Heat exchanger outlet control and performance monitoring. Precision control in blending, reactors, or steam tracing validation. HVAC and environmental control systems. Also suited to differential temperature measurement in high accuracy loops, temperature compensation in density viscosity-based flow measurements. Construction and sensor configuration, sheathed assemblies, mineral insulated stainless steel sheaths with embedded RTD wire, mounted inside thermowells for mechanical protection and easy replacement. Wiring types, 2-wire, basic, prone to lead resistance error, rarely used. 3-wire, compensates for lead resistance, common in industrial settings. 4-wire, high precision applications, fully compensates for lead wire resistance. Head-mounted transmitters convert resistance signal to 4 to 20 milliamps analog or digital HART. Provide galvanic isolation and cold junction compensation. Installation and integration best practices. Thermowell use. Always install RTDs in thermowells, selected per DEP piping class. Avoid undersized wells, which can delay sensor response time. Ensure minimum immersion depth of 10 to 12 times well diameter for accuracy. Orientation and mounting. Position horizontally or angled upward to prevent water ingress into the sensor head. Protect assembly head from rain, spray, and mechanical impact. Loop configuration. Use screened cables, proper grounding, and avoid high EMI zones. Use transmitters with galvanic isolation between sensor and output circuit. Advantages over other temperature sensors. Higher accuracy and linearity than thermocouples over moderate temperature ranges. Repeatable, drift-free performance in clean, controlled environments. Easily integrated into digital control systems via intelligent transmitters. Ideal for narrow span or differential temperature applications. Limitations and engineering considerations. Not suitable for high vibration locations, wire breakage risk, very high temperatures, 650 degrees Celsius, loss of calibration stability, rapid transients, slower response than thermocouples in some configurations. Requires proper sensor placement and immersion for valid readings, 4-wire wiring or signal conditioning for high accuracy circuits. Care in element material selection to avoid chemical attack. Good practices and optional features. Use duplex elements only where redundancy is required. Avoid using for control plus IPF split. In custody transfer, ensure batch calibration and certification to traceable standards. For averaging measurement, e.g. tank profile, install multi-point RTDs inside protective wells. Maintain uniform wiring and transmitter configuration across installations for data consistency. Conclusion. Resistance thermometers offer unmatched accuracy, reliability, and integration flexibility for critical industrial temperature measurements. Their stability and precision make them the gold standard for applications where measurement certainty matters, such as fiscal metering, process optimization, and energy balance calculations. With proper protection and installation, RTDs provide years of drift-free performance and seamless control system integration. Machine monitoring instruments for predictive protection and condition-based maintenance of rotating equipment. Purpose and functional role. Machine monitoring instruments enable real-time surveillance of rotating equipment, protecting assets such as turbines, compressors, pumps, and blowers. By continuously measuring key mechanical parameters like vibration, shaft displacement, and bearing temperature, these instruments provide early warnings of degradation, allowing safe shutdowns, targeted maintenance, and performance optimization. Key monitoring parameters and instruments. Radial vibration sensors detect shaft vibration perpendicular to the axis of rotation, reveal issues like imbalance, shaft misalignment, or bearing wear. Typically non-contact eddy current proximity probes. Axial shaft position, thrust probes. Monitor axial displacement of the rotating shaft. Indicate thrust bearing degradation or axial loading faults. Bearing temperature sensors. Measure temperature at thrust and journal bearings. Rising temperatures signal lubrication breakdown or overload, typically platinum RTDs or thermocouples installed in bearing shoes. Key phaser probes, optional, provide angular shaft position reference, used for dynamic diagnostics like orbit analysis and phase comparison. Detector monitoring system architecture. Modular rack-based monitors, installed in protective cabinets, typically in control or auxiliary rooms. Each monitored point, vibration, position, temperature has an independent processing channel, equipped with trip relays, set points, and signal outputs for alarms. Signal conditioning. Oscillator demodulator modules convert raw signals into actionable outputs. Analog and digital outputs support integration with control or safety systems. System integration. Output signals connect to plant systems for real-time display and trending, alarm handling and automated trips, historical logging for diagnostics and maintenance planning. Applications and use cases. High-value equipment. Compressors, turbo expanders, high-speed pumps, generators, machines where failure results in costly downtime or safety risks. Failure prevention, early detection of mechanical defects, rotor unbalance, loose components, fluid-induced instabilities, seal or bearing degradation. Condition-based maintenance, extends asset life by tracking degradation trends, replaces fixed service intervals with targeted intervention. Selection and design considerations. Channel separation. Use dedicated, isolated channels for each parameter, no shared circuits. Ensures reliable operation and simplifies diagnostics. Response time. Monitors must react instantly to exceedance of critical limits. Trip logic should include time delays or suppression logic for startup phases. Redundancy. Apply dual sensors or backup channels for protection critical equipment. Reduces false trips and improves reliability. Power supply. 24 VDC floating supply is standard. Systems must tolerate brownouts, switchovers, and battery transitions. Installation and operational best practices. Sensor placement. Mount vibration and thrust probes as close as possible to bearings. Maintain correct probe gaps, orientation, and shaft runout clearance. Mechanical integrity. Probes must be rigidly mounted on low vibration surfaces. Avoid long, unsupported extensions or poorly anchored brackets. Cabinet location. Monitoring racks should be housed in low noise, temperature controlled rooms. Avoid exposure to vibration, dust, or moisture. Maintenance access. Install monitoring hardware with front access for channel testing and replacement. Provide test sockets for signal simulation and phase analysis. Advantages over conventional monitoring. Continuous real-time protection during operation and transients. Captures early-stage mechanical issues before they escalate. Enables automatic protective actions. Trips, alarms, interlocks. Reduces unplanned downtime and optimizes machine availability. Limitations and precautions. Requires correct sensor alignment and calibration to function reliably. Sensitive to electrical noise, proper shielding and cable routing is critical. May require alarm suppression logic during startups or coast downs to avoid false trips. Must be periodically tested to confirm function and response thresholds. Flame detection instruments for safe operation and automated shutdown of combustion systems. Purpose and functional role. Flame detectors ensure safe ignition and sustained combustion in fired equipment such as furnaces, boilers, heaters, and incinerators. They continuously verify flame presence and initiate alarms or automatic fuel shutoff if flame loss is detected, preventing unburned fuel accumulation and potential explosions. Key flame detection technologies: ultraviolet UV detectors. Detect UV radiation in the 180 to 260 nanometers range emitted by hydrocarbon flames. Very fast response time, milliseconds. Sensitive to arc welding and lightning, requires logic filtering. Infrared IR detectors. Sense flame-specific IR flicker, typically 4.2, 4.6 micrometers for hydrocarbon combustion. Immune to sunlight and electrical arcs. May require line of sight and clear optical path. UV-IR combination detectors. Combine both UV and IR sensors to increase discrimination and reliability. Reduce false alarms from external radiation sources. Multispectrum IR MSIR detectors use multiple IR wavelengths to identify flame signatures, excellent immunity to false alarms, and high reliability in difficult environments. Applications and use cases: fired heaters and process furnaces, monitor pilot and main burners for continuous flame, interface with burner management systems for safe start-stop sequencing, boilers and steam generators, ensure flame presence during startup and combustion cycles, required for automatic shutdown under loss of flame conditions, incinerators and waste gas burners, detect flame in open or variable flow burners, may require rugged wide-angle sensors due to flame instability. Special services, sulfur recovery units, SRUs, or H2S combustion require detectors designed for low radiation or low luminosity flames. Selection and design considerations. Fuel type compatibility. Flame characteristics vary by fuel, e.g. natural gas, diesel, H2S. Select detectors matched to spectral output of expected flames. Detector field of view. Must have unobstructed line of sight to flame zone. May require multiple detectors to cover all burner tips. Ambient conditions. Detectors must operate reliably in high temperature, dusty, or humid environments. Optics should be protected from fouling and fogging. Air purge requirements. Many detectors need clean, dry purge air to prevent lens contamination and overheating. Positive airflow should be filtered and maintained at consistent pressure. Response time and reliability. Detectors should trip fuel shutoff within 1 to 2 seconds of flame loss. Built-in diagnostics to detect lens fouling, sensor aging, or circuit faults. Installation and operational best practices. Mounting orientation. Position detectors for direct sight of flame core, avoiding reflections or glare. Use vibration-resistant brackets and allow easy access for maintenance. Self-check capabilities. Select models with continuous self-diagnostics and fail-safe output. Systems should provide fault alarms for dirty optics, sensor failure, or signal loss. Wiring and signal output. Use shielded armored cables routed away from EMI sources. Signal types include relay contacts, 4 to 20 milliamps analog output, or digital protocols. Test and verification. Include flame simulators or built-in test sources to validate detection circuits. Perform functional checks during shutdowns or scheduled maintenance. Advantages over conventional methods: rapid response to flameout conditions, protecting personnel and equipment, automatic shutdown to prevent unburned fuel hazards, high sensitivity to real flames. Some models can detect invisible flames, e.g. methanol. Adaptable to various fuels and burner designs. Limitations and engineering precautions. False alarms may occur from welding arcs, hot surfaces, or flare reflections, mitigated by spectral filtering or logic delay. Obscured optics, e.g. from soot, fog, or steam, reduce detection reliability, requires purge or maintenance access. Not suitable for buried or shielded flames, must maintain optical line of sight. Detector lifespan may be reduced in high vibration or corrosive environments, requires ruggedized housings.